Hmm. Class, my computer is being weird. Am I streaming? I don't even know if I'm streaming right now. Um, Sorry, I just want to make sure that I'm actually online before I start. Okay, it looks like I am. Someone said good morning to me. All right, so I'm going to go ahead and get started. So we are talking about experimental physics today, and I am going to um, go ahead and uh, review energy and momentum today and possible experiments that you could do with energy and momentum. So first I'll talk about energy. And we learned about um, three different types of energy. There was kinetic energy, which is the energy of motion. We learned about gravitational potential energy, which is the energy because of your location in a gravitational field. And we also learned about elastic potential energy, which is the energy contained in a stretched rubber band. Now, the important fact about energy is that E initial is E final. So the total initial amount of energy does not change as time goes on. So oh my gosh. Do you ever go like this? You go, and then like a booger goes back down into the back of your throat and it's stuck there. That's what just happened to me. I just went, and then a booger just went onto the back of my throat. And now it's stuck there. Okay, I think it's cleared. Wow, that was gross. Okay, so you have a. By the way, I realized that once we return to school, I'm going to have to be wearing a mask. And so, how will I smile? Right? Everyone is going to have to smile using their eyes only. Right? So, I've been practicing. Okay? Do I look like I'm smiling? Okay. So, practice your eye smiles, everybody. Okay, so we so what we would do, here's a really basic experiment. We have a block and we let the block slide down to the bottom. Okay? And we measure its initial height, which is, I'll call it y, and then we measure its speed once it's at the bottom. Okay? And then what we would do, because when we do an experiment, we never just do one trial, we do multiple trials, okay? So maybe we start the block at different heights. So we start it right here. So maybe this is y0, this is y1. Maybe we start it right here. And so y2. And so by starting the block at different heights, okay, starting the block at different heights, we can develop a data table of y, height, versus v. Okay? So now the question becomes, what should the relationship be? All right? So when I say what should the relationship be, applying the equations of physics, what should, how are these two variables related to each other? So we're going to use conservation of energy. Initial energy equals final energy. And then the initial energy is gravitational potential, so that is mgy. The final energy is 1/2 mv squared. It's kinetic energy because it's moving. All right. I'm going to cancel the m's out because there's an m on both sides, and I'm going to multiply both sides by 2. And that gives me the following theoretical relationship between the variables. Okay? So notice how when I derived this theoretical relationship, see how it has v squared and y. So it doesn't have v and y, it has v squared and y. So what I'm going to do is I am going to transform my data table. So maybe this is like 1, 2, 3, 4, and this is 1, 2, 3, 4, something like that. This isn't real data. But I'm going to transform it into a data table of y versus v squared. So I'm not squaring y, so I still have 1, 2, 3, 4. But I am squaring v, so I have 1, 4, 9, 16. Okay? So I transform that data table because that is the way it appears in the equation. So, and then that's also the way I'm going to graph it. U sub g is gravitational potential energy. U sub e is elastic potential energy. So I'm going to put v squared on the vertical axis, and I'm going to put y on the horizontal axis. Okay? So now what we want to do is we want to figure out what is the meaning of the slope of this graph. Okay? So I have v squared on the vertical axis. So I'm going to replace v with y. Okay? And then I have y on the horizontal axis. So I'm going to replace y with x. And then I can see that the number that is multiplying x is 2g. All right? And so looking at the standard equation of a line with an intercept of 0, it's mx equals y. So by comparison, I can see that this should be a straight line, and the slope of that straight line should be 2g. So this is the theoretical prediction of what the relationship between those two variables should be. So 2g is, because g is about 10, the slope should be 20 or so. Now, that doesn't mean that you're going to actually get this. You might get something different. In fact, I would expect that you probably get something that looks like this. So I bet you would get something that does look like a line, but it has less of a slope, okay? So this is sort of theory, but usually there's a difference between, or there is at least a small difference between theory and experiment, okay? And so what we might do is we might try to explain that difference. And so the reason that I think that that would be what would actually happen is because we are neglecting an important factor in this analysis, which is friction. And friction has the effect of slowing the block down. So these speed values are not going to be as big, and so the actual line might be a little bit below the theoretical line. Okay? So that could be an explanation for the difference between theory and experiment. All right? So that's what we have to do. We have to compare theory with experiment, and then if we think the theory is right, then we have to explain why the experiment was different. Or if we think the experiment was right, we have to change the theory to accommodate that. Okay? So so we have to try to explain why there's a difference. Let me give you another experiment that you could do involving energy. What if you had a spring, and that spring is attached to a mass, and that spring is compressed a distance a, all right? And then the mass is released, okay? So the spring decompresses, and in the process, it launches the mass with some speed, which we will call v. All right, so now the question is, what are you varying with each experimental trial? So are you kind of like this one, we varied the height. And in this one, we kind of have multiple options, okay? We could vary the mass of the thing that we're launching, or alternatively, we could vary the amount that the spring is compressed before launching it, okay? So I'm going to assume that we varied the amount that the spring was compressed before launching it. So that would mean that the data table that I collect would be amount compressed, and then I measure the velocity in response to that. Okay? So I do a bunch of different compression amounts, I get a bunch of different launch speeds. So now the question becomes, what should be the relationship between these variables if we apply the equations of physics? Okay? So the theoretical relationship. Well, I use conservation of energy. So initial energy equals final energy. And the initial energy is the energy of the compressed spring. So that is elastic potential energy, 1/2 kx squared. The final energy is the kinetic energy of the launched mass, 1/2 mv squared. Okay? I cancel out the 1/2. And I'm going to divide both sides by m, and that gives me k over m. Oh, this is actually, I wrote x here, but this is actually a, right? The amount compressed. A squared equals v squared. So at this point, we could just leave it as is, but notice how v squared and a squared appear in this equation. So that would mean that if I wanted to graph this, I would have to transform my data table into a v squared versus a squared data table. Okay? But I'm too lazy to do that, so I'm not going to do that. Okay? What I'm going to do instead is I'm going to take the square root of both sides, and I get square root of k over m. Square root of a squared is just a, equals v. All right? So, there you have it. And so what this says, see how it's v to the first power and a to the first power. That's exactly what I have here in my data table. So I don't need to change my data table like I did in this example, okay? Because the theoretical relationship just had a and v just as they are, okay? So so that means I'm going to graph launch speed on the vertical axis and amount compressed on the horizontal axis. And so launch speed is acting like y, amount compressed is acting like x, and the thing that is multiplying x is square root of k over m. Okay, so that means that the theoretical relationship is a straight line, and the theoretical slope of that is square root of k over m. Okay? And that's how it works. So, as I said, most of the time, the velocity is going to be reduced from the theoretical value because of friction. And so again, I would probably expect that it's going to be something with a smaller slope is what you would actually get. Okay, so that's a little review of energy. Energy transforms from one type to another. And so now let's talk about momentum. Momentum is denoted by P, and the formula for momentum is P equals m times v. Okay. The momentum is conserved, so that means that the total initial momentum is equal to the total final momentum. All right, and when I say total momentum, I mean the sum of the individual momenta of the parts of the system. Okay, so here's a possible experiment you could do. So you have a mass m2, and it's just at rest, okay? Then we have a mass m1, and we slide it to the right with an initial speed v naught. And let's say we put tape like on the front side of this mass so that when the two masses collide, they stick together. So after they collide, they are now stuck together. So we have 1 and 2, and they have some final velocity, v final, like that. Now there are lots of things that we could vary from trial to trial in this experiment. So we could vary the masses, we could vary the speeds, we could vary a mass and a speed, or there's all kinds of different combinations for what we could measure and what we could vary. But I'm going to assume that we are launching M1 at M2 with different initial speeds. Okay, so that means that in our data table, we have V initial is the first thing that we measure, and then the speed after the collision is the other thing that we measure. Okay, so the masses are staying the same with every experimental trial. So we get some data points, some ordered pairs. Okay, so what should the theoretical relationship be? All right. So P initial equals P final. The initial momentum is carried only by the mass M1 because M2 is at rest. So my initial momentum is M1 the initial. Okay. And after the collision, these two are stuck together. So they're acting like a single mass of total amount M1 plus M2. And their speed is V final. So now I'm going to divide both sides by M1 plus M2. So I have M1 over M1 plus M2 times V0 equals V final. So I can see that there isn't anything fancy happening. I don't have V initial squared or V final squared or V final cubed or anything like that. I just have V initial and V final. So that means that I don't have to transform my data table. I just leave it as is, and I just straight up graph V final versus V initial. Okay? So V final is acting like Y. V initial is on the horizontal axis, so it is acting like X. And then the thing that multiplies X is the slope. So that means that this data should look like a straight line, and the slope of that straight line is going to be M1 over M1 plus M2. Okay? So, like, if you wanted to confirm the conservation of momentum, what if you wanted to, you would expect that this data should look like a straight line. And then after the experiment, what you would do is you would measure the masses M1 and M2. And you would compare that, you would compute this, and you would compare it to the slope of the line of best fit and see if they're the same. If they're the same, you would say, all right, I have strong evidence that momentum was conserved in this collision. All right. Probably what will happen is, again, because of friction, as time goes on, friction slows things down. So I would expect the final velocity would be less than what is expected. So you might get something like this. Depends on how slippery these surfaces are. If you had really, really, really slippery surfaces, then the slope might be really, really, really super duper close to what you expect. Here's another experiment with momentum. You have a system. You have two masses. You have M1 and M2. And in between those two masses is a compressed spring. Okay, and the system starts out at rest. Okay, but this spring is compressed. It has all this elastic potential energy. It's ready to go. Okay, and so at some later time, you let the spring do its thing. It goes wow, 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 wow. Okay, so the spring does its spring thing and decompresses, and M1 gets launched this way, and let's say it has a speed V1, and then M2 gets launched this way, and it has a spring or a speed V2. Okay? So once again, there are lots of different things that we can vary from experimental trial to experimental trial. We could vary the masses. We could vary the spring itself. Springs of different stiffnesses. We could vary the amount that the spring is compressed. Okay. So what we are going to measure for this experiment is we're going to measure the final velocity of 1 and 2. Okay. So basically, we collect the final velocity of the first object and the final velocity of the second object. That's what we choose to check. Now, how do we vary this? How do we get different velocities? Well, to get different velocities, you would compress the spring by different amounts. Okay? If you compress the spring more, it's going to launch these faster. And so you would expect bigger numbers. Okay? If you compress it less, these are going to be smaller numbers. So you compress it different amounts, and you let this spring launch the things, and you measure the two speeds. Okay? So what is the theoretical relationship between these variables? Theoretically speaking, initial momentum is final momentum. The initial momentum, because they start out at rest, and momentum is mass times velocity. If you're at rest, the velocity is 0, and so your momentum is 0. Initial momentum is 0. Final momentum is the momentum of mass 1, which is going to be m1 times v1, plus the final momentum of mass 2, which is m2 times v2. So then I can subtract m1 v1 over to the other side, so I have minus m1 v1 equals m2 v2. And then I divide both sides by m2, and that gives me minus m1 over m2 times v1 equals v2. So we can see that v1 and v2 both appear in this theoretical equation. They're not squared. They're not squared. They're just as they are. And so for that reason, we don't have to do any transformations of our data table. We can simply graph it as is. So I'll put V2 on the vertical axis and V1 on the horizontal axis. So then we can see that V2 is on the vertical axis, so it is acting like Y. V1 is on the horizontal axis, so it is acting like X. And then the thing that is multiplying X is minus M1 over M2. So I expect this data to be a straight line, and the slope of that straight line is minus M1 over M2. All right. I think that this experiment would actually be pretty accurate. And the reason is that both of these velocities are measured at the same time. So they might both be slowed down, or they might by friction, but the thing is they're slowed down by friction, but they are both slowed down by friction. So we kind of would expect that they are both altered from the theoretical value in such a way that those cancel each other out and you end up getting the same relationship. Okay? I don't know that for sure, though. This is kind of a tough experiment to do. Momentum experiments are tough to do without the presence of friction. All right, so that is my lesson for today, and I want to see you in the Zoom room for I'm going to review one more time how things are going to work for um, when we go back to school. Okay? So I will see you soon. Bye-bye.